Hey there, students. In this clip, we're going to be going over an example on how to use the additivity rule for definite integrals using the integration rules, and then also making use of geometry and evaluating definite integrals. Okay. After I give you the example, then I'll give you a sample problem to try out to demonstrate your understanding. All right. So let's take a look at the question. Example one. If f of x is a piecewise defined function, okay? So if f of x are given by 8x, when x is between 0 and 1, and then 8 uh, when x goes from 1 all the way to 8, and then x if when x goes from 8 all the way to 14. Okay, so this is what f of x is. Find the definite integral from 0 to 18, to 14 of f of x dx. Okay, so we're going to do this using two different methods. First of all, I'm going to use geometry, and then I'll finish this up using the techniques of integration. Okay, all right. So in order for us to use geometry to evaluate this integral, we need to be familiar with how to generate piecewise defined functions using the function. We need to know how to generate the graph using the equations. All right. So let's go ahead and graph this curve. So we have 1, 2, 3 functions that we're going to be graphing. So let's set up our coordinate system. We're going to go from 0 to 14 on our x, and then determine how high we're going to be going. Basically, maybe as high as, let's figure that out in a minute. So we're going to go as high as 14 because this function goes from 0 all the way to 8. As high as 8 stays constantly 8. And this goes from 8 all the way to 14. So as high as 14, that's how we'll set up our graph. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. All right, let's set up our coordinate system. There goes my y, and there goes my x-axis. All right, to calibrate my x-axis, I'm going to use units. So this is 1, 2, 3, 4, 5. This is 5, 6, 7, 8, 9. This is 10, 11, 12, 13, 14, and this is 15. All right, and then for my x-axis, I'm going to go by 2s. I'm going from 0 to 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, because if you look at the constraints on our x's, for the function, we're going from 0 all the way to 14. All right? Okay, so from 0 to 1, from 0 to 1, we have, right, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so let's graph the first function. The first function is 8x. So for that one, y equals 8x. It's a line. The slope is 8 over 1, and the y-intercept is 0. Okay, so it's 8x plus 0. So starting from 0, we're going to rise 8 and run 1. Okay? All right, so let's do that. So starting from 0, we're going to rise 8. Starting from 0 here, that's the y-intercept. That's the point on the line. Rise 8 and run 1. So that's the point for the first line. Let's go ahead and graph it. First line goes from 0 all the way to 1. All right, the second line is constantly 8. F of x equals 8, so it's going to be a horizontal line from 0 to 8. So we have a horizontal line from 0 all the way to 8. And then the last line is just x, y equals x. Let's write that down, y equals x. In this case, x plus 0, the slope is 1 over 1, and the y-intercept is 0, so you're going to rise 1 and run 1 from 8 all the way to 14. So from 8, we rise 1, run 1. It's slightly skewed in the exaggerated on the y direction because in the x direction because 2 boxes correspond to 1 unit in the x direction. Okay, so rise 1, run 1, 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 rise 1, run 1. Okay, see how it lines up with the 14? So from 8 to 14, that's the last function that we have, okay? So there goes the graph of our piecewise defined function. If you notice, we can break this into 3 sections. Let's break it up. This is the first section right here. This is the second section right here. And this is the third section. Now, if you think about what a definite integral is, it's basically the area under the curve, right? So if you take a look at this and your task is to find the area under this curve, you note that you can simply use the tools of geometry to figure out what's the area under this curve is. You don't need any complicated calculus formula. Okay, so what we're going to do is use the geometrical tools we learned in geometry to find the area first, and then reinforce the accuracy of our results using integrals, the rules of integration. Okay, all right, so let's label it. So let's call this A1, the area under the curve in region 1, A2, the area under the curve in region 2, and then A3, the area under the curve in region 3. Okay, so in region 1, we have a triangle. All right, so for a triangle, you need to use the formula half base times height. So in this triangle, the base is 1 unit long, and the height is 8 units long. Okay, 1, 2, 6, 7, 8. That's 8. Okay, so that's for the triangle. And here in region 2, we have a rectangle, and we know the area of a rectangle is length times width. So the length of this rectangle, L, is equal to from 1 to 8 is 7 units long, and the width, W, is going to be, let's put it right here, W is going to be 8 units long, also 8 units. Okay. All right, for our region 3, we have a trapezoid. Okay, for a trapezoid, we know what the area of a trapezoid is 1/2 base 1 plus base 2 times height. So the bases are the parallel sides. So in this case, this is base 2. Base 2, 1, 2, 3, 4, 5, 6, 7, 8. Well, I'm supposed to be counting by, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Base 2 is 14 units long. And then base 1 is 8 units long. Okay, and then the height is the length from 8 to 14, which is 6 units. So the height, h, is going to be 6 units. Okay, all right, so the integral from 0 to 14 of our function is basically a1 plus a2 plus a3. Okay, the areas under the curve is what we're looking at here. All right, so let's input the formulas. For region 1 is going to be 1/2 base times height. Region 2 is going to be length times width for rectangle, and then for region 3 is going to be 1/2 base 1 plus base 2 times the height, the perpendicular height. Okay. All right, let's input our values into the formulas and compute what the integral is. Okay, so it's going to be 1/2 base here is 1 times the height of 8 plus in the second region the length is 7 times the width, which is 8, plus in the last one 1/2 b1 is 8 and b2 is 14 times the height, which is 6. Okay, all right, now let's compute this. This is going to be 4 plus 56, and this is going to be plus 8 plus 14 is 22, divided by 2 is 11 times 6, 66. add the whole thing, you get 126. All right, so this is your area. Okay, let's do this using integrate the rules of integration method 2. We're going to be using integration techniques, okay? All right, so method 2, we're using integration techniques. Method 1 was using geometry, okay? Integration techniques. All right, let's do this. So it looks like we're simply going to be using the power rule repeatedly and constant rule once. So the integral from 0 to 14 of f of x dx, we're just going to break down the function into the respective regions, okay? So for region 1, we're going to be integrating from 0 to 1. What function exists in region 1? This piece right here is 8x, right? So the first function is going to be 8x dx plus region 2, we're going to integrate from 1 to 8. And the region that's a horizontal one, which is simply 8 dx plus the last one, we're going from 8 to 14, and that was x dx. Okay? All right, now let's evaluate the integrals one by one. We're going to be using FTC part 1 here. So integrate that using the power rule is going to be 8x squared over 2, evaluated from 0 to 1. And then the next one will be the antiderivative of 8 is simply 8x, evaluated from 1 to 8. And then last but not the least is the antiderivative using the power rule for x is x squared over 2, evaluated from 8 to 14. Okay? All right, let's evaluate these, each and every one of these one by one. This can be reduced because 2 goes here once and 2 goes here 4 times. So we're going to have 4 times 1 squared minus 4 times 0 squared for the first one, plus, and then applying FTC part 1 on this one, we're going to have, let's see, 8 times 1, 8 minus 8 times 1. And then for the last one, we're going to have 14 squared over 2 minus 8 squared over 2. Okay? Alright, so if we evaluate this, you simply get this whole thing is 0. So we have 4 plus 8 times 8 is 64 minus 8 plus, and in this case, 14 square is 196. 196 over 2 is 98 minus 8 squared is 64 over 2 is 32. Alright, so it becomes 4 plus 64 minus 8 is 56, and 98 minus 32 is 66. Add everything together, you get 126. Okay, so there goes your final answer. You see that our answers are in fact correct. Okay, so there you have it. All right, so how well did you understand this example, or have you mastered it? Well, what I'd like you to do is try this question, example 2. If f of x is a piecewise defined function given by 2 when x is between 0 and 2, and 3x minus 4 when x is between 2 and 3, and then 1/3 x, let's do it properly, 1/3 x plus 4 when x is between, goes from 3 all the way to 6. Okay, so if this is what f of x is, a piecewise defined function, find the integral, the definite integral from 0 to 6 of f of x dx using geometric and algebraic methods. Okay, algebraic methods. When I say algebraic methods, I'm talking about integration techniques. Okay, integration techniques. All right, so what I want you to do is try this example out, and in the comment section of this video, post an answer, or if you have any questions, let me know what it is, and I'll be glad to help you out, okay? So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here so you can get updates to more cool math clips such as this. And also post a comment, like I said earlier, to indicate your response, your answer to the question, or how you feel about this clip, what you got and what you didn't. And for more calculus clips, you can go to mathgotserved.com/calculus, so you can just scan this QR code for direct access. Thanks again for watching, and have a wonderful day.